All right, in this tutorial, we're going over the Algebra 2 Big Ideas section on Chapter 2.1, Transformations of Quadratic Functions. So being able to describe transformations of your quadratic functions and write your transformations of the quadratic functions, either in the form of a graph or adjusting an equation, or just simply stating, shift 4 to the right or something similar to that is all we're going to talk about this chapter. So we kind of talked about the different types of parent functions in 1.1 and 1.2. More specifically, Chapter 2, we're going over quadratic functions. So that's a function that can be written in the form of f of x equals a times x minus h squared plus k. So the a and the h and the k are all numbers that could be adjusting your parent function. But as long as you have an x and a exponent of exactly 2, it is a quadratic function. The U-shaped graph of that quadratic, you'll hear me call it a parabola quite frequently. So a couple different types of translations are horizontal and vertical, so left and right, up and down, just moving. The horizontal translations, similar to how they were being interacted in the linear and absolute values that we went over last chapter. Any number that is being added or subtracted inside your parentheses is always going to be moving in the opposite direction. So starting out with this black parabola at the origin, if you were to shift this to the left, that would be subtracting a negative number. And when you ever have two negatives like x minus -2, that can be rewritten as a positive. Same thing over to the blue. So if you're shifting to the right, then that means you're shifting in a positive direction. So it would become x minus 2 or x minus 3. And that minus stays there because minus a positive number just stays minus. Then vertical is you do exactly the way you see it. So anytime you're adding a number k to the outside or your outputs, if you're shifting up, that k is going to be positive. So let's say you're going up 2, this would be x squared plus 2. Then to go to the red equation, if it was less than 0 or negative, then it would just be x squared minus 2 to indicate down. So horizontal, inside the parentheses is opposite. Vertical, outside, you do exactly what you see. So let's describe the transformation of just the parent function x squared and how we would get the g of x plus 4 squared minus 1, and then graph each one of those functions. So given that basic form that we went over on the previous slide of x minus h squared plus k, we need to rewrite that function to identify h and k. So remember, h and k help indicate where you're shifting the graph. So that h is going to be a minus 4 because it always needs to be minus on the inside. And your k is going to be a -1, and that's exactly the way you see it. So this graph is being shifted to the left 4, and it is going down 1. So the black graph is your basic parent function of x squared. Your blue one is what happens after you shift, just looking at this vertex point, left 4, down 1, and there's where you get the function g of x. So now on to reflections. You have two different types. You have a vertical and a horizontal reflection. So if you reflect across the x-axis, that is the vertical direction, so you're flipping it up and down, and that means you are affecting the outputs. So it would happen on the outside of the equation, which would be negative. The most basic type of reflection you'll see from your parent function is to flip it down and just put a negative in front. Your x values will stay the same, but your y values now become negative because there's a negative being multiplied in front. Reflecting over the y-axis, the most interesting thing about parabolas is that they have a line of symmetry vertically going through the vertex. So all of your points to the left can be reflected exactly over to the right. So if it happens to line up on your x-axis, or on your y-axis, sorry, and you're reflecting over the y-axis, you're going to get exactly the same thing. So notice how you're changing the inputs inside this parentheses by multiplying by a negative. And whenever you square a negative number, you still get a positive. So it doesn't matter what's happening on the input, you're always going to get a positive number. Then for stretches and shrinks, so remember horizontal, that is happening inside the equation or your inputs. So you need to put parentheses around that number that you're multiplying inside. And if you have a number greater than 1, that's the opposite, where it's going to compress horizontally. And then if you have a number that is less than 1 or a fraction, that is a horizontal stretch and is pulling apart. Vertical is you do exactly what you see. So on the outputs, if you're multiplying by a number greater than 1, that is a vertical stretch and they're being pulled apart from each other. And then if you're multiplying by a number of less than 1 or a fraction, that is a vertical shrink or a vertical compress. All right, let's describe the transformation of x squared to get to g with multiple parts and then graph each one. So notice that in part A, g of x, the function is in the form of negative ax squared, where your a is 1/2 with a negative in front of it. So it's not a negative 1/2. The negative corresponds to our reflection and the a responds to our stretching and compressing. So since the graph of g is a reflection over the x-axis, then the 1/2 makes it a vertical shrink because it is less than 1. So those are your two transformations, a vertical or reflection over the x-axis, and then a shrink of 1/2. So starting out with the basic parent function of x squared, you're going to flip it down and then vertically shrink it, which really on this limited graph window just makes it look like things are spilling out the side because you're compressing it down vertically. Moving on over to part B. So in g of x, you have 2x squared plus 1. You are given that 2 inside the parentheses, so that should be telling you what's happening horizontally. And then that plus 1 is outside the parentheses for your k. So since that a is on the inside, it is a horizontal shrink. And again, it's always the opposite of what you see on the inside, so you need to flip that and make it 1/2. Then that 1 is on the outside. Vertical is you do exactly what you see, so that is being translated 1 unit up. So first, you're going to take your basic parent function, horizontally shrink by a factor of 1/2. So you're going to take the horizontal sides and bring them together, which makes it spill out more on the top. And then you're going to move that graph up 2, or up 1, sorry, because your k is 1. Remember to follow your PEMDAS. A is being a multiplied, so that goes first, and then your plus 1 comes after that. Do not shift the graph up 1 and then compress. Sometimes that order may make things confusing, so just follow your PEMDAS. All right, so the lowest point of a parabola, if it opens up, or the highest point on a parabola if it opens down, is called the vertex. So the vertex is pretty much your h and your k. So if you're given a basic form of the ax minus h squared plus k, whatever number is in your h is the x coordinate of your vertex, and whatever number is in your k spot is the y coordinate of your vertex. So let's let the graph of g be a vertical stretch by a factor of 2 and a reflection in the x-axis, followed by a translation of 3 units down of your basic parent function x squared. Let's write a rule for g and then identify the vertex. So first we're going to identify how the transformations are affecting the constants that are in vertex form. So the constants are your a, your h, and your k. Well, you have a reflection, which is going to make a number negative out in front. You have a vertical stretch by a factor of 2. So that a is going to be a 2. Then it is followed by a translation of 3 units down. So since that's a vertical translation, you do exactly what you see and make that a -3. So we're just going to plug those numbers into our a x minus h squared plus k. H is 0 because we were not told any horizontal translation. We're not shifting left or right at all, so that stays the way it is. Your -2 comes from the a, and your -3 comes from the k. Simplify things all the way down to get -2 times x squared minus 3 as your new graph of g of x. Then just looking at what your h and your k positions are, since your h is 0, that's your x coordinate of the vertex. Since your k is -3, that's the y coordinate of your vertex. So another way you could do is to begin with the parent function and then apply the transformations one at a time and see how that is affecting your equation. So write a function with h that represents the reflection. So multiply by that -2 for the reflection and the vertical stretch. So you get -2x squared. That's what the equation looks like just with the flip and the stretch. Then you write the function that has that translation of the h of x. And that means you're going to take that previous function, subtract 3 from the end, and you just get -2x squared minus 3. And then if you look on the inside of your graph, your h is still 0, your k is -3. So either way, depending on the order, it doesn't really matter. You end up with the same thing. It just depends if you're more comfortable with looking at these one equation at a time, or going through and putting all the translations together and then affecting your basic equation. We can click through these. Okay, so let graph of G be a translation of 3 units to the right and 2 units up, followed by a reflection in the y-axis, starting with our basic parent function of f of x equals x squared minus 5x is what we're starting with. So we could first write a function that represents the translation of 3 units right and 2 units up. Got your x minus 3 plus 2 of the basic function. So we're going to plug in x minus 3 into wherever we see an x, and then add 2 at the end. So we're rewriting, instead of x squared, it's x minus 3 squared. And instead of minus 5x, it's minus 5x minus 3 with a plus 2 at the end. Okay, remember when we're going to multiply these out, we can either FOIL or use the box method, but you're going to end up with x squared minus 6x plus 9 for what's just inside these parentheses. And then you combine like terms after the distribution of negative 5x plus 15. And when you add all your constants of 9, 15, and 2, you get 26. And then when you combine your negative 6x and your negative 5x, you get negative 11x. So there is your equation right there. Then you're going to write a function that represents the reflection, so that you're just going to multiply by negatives on the inside of all of your equations. Don't forget to put the parentheses around your x. Remember, whenever you square a negative number, you're always going to get a positive, so that stays positive. But this negative 11 times negative x does affect this and make it positive, so it does look a little bit different. All right, using a modeling question for the final example. So the height h in feet of water spraying from a fire hose can be modeled by h of x equals, and you can read that equation from there. X is going to be represented of the horizontal distance from the fire truck. So the crew is going to raise the ladder so that the water hits the ground 10 feet further from the fire truck. Let's write a function that models the new path of water. So we're already given the equation of what the fire truck is starting to spray the water at. But then what they're going to do is they're going to move it so that the ladder is 10 feet further from where the fire truck is. How does that affect the water? So then we need to analyze the graph of that function from the first one to determine what the translation needs to be in the equation so that the ladder is pushing the water 10 feet further. So when you use a graphing calculator or when you use your Desmos and type in that negative 0.3 equation, this is what it's going to look like. So your water is starting to spray right here, and it ends up hitting the ground right here at this point. That point is called the 0, and whenever your y is equal to 0, that's when that's coming all the way down and hitting the ground. So because 50 is the x distance, or the horizontal distance of where that water is coming down to hit the ground, the range is what's affected by anything that is going down below that. Now in a real life situation, your fire truck water is not going to go through the ground and keep going down even further negative. So we don't need to include any of our negative values. We really are just only looking at this path right here as soon as it hits the ground. But in terms of the graph, if you keep observing and look what happens at 60, you get a negative 23 on your y-axis. So then you can determine that when you translate this 23 units up, or 23 feet up, That is the difference of the 10 from your 50 to your 60, because we're adding 10 from the 50 to get 60, which means that your vertical change has to be 23 feet. So when you use that graphing calculator to make that adjustment from your original function, this is what it's going to look like. So then your water that originally hit the ground 50 feet from the fire truck, again, range doesn't matter because we don't care about what happens after the water hits the ground, even though hypothetically it would continue. All you need to do is just add that 23 units to the end of your equation, because that's how far you need to shift up. And then you only are adding your constants. So your 23 to your previous equation would get you that 48 from there. So that's the path of the water. If you check that and plug it back in, you plug in your 60 of this, 60 squared times negative 0.3 plus your 60 again to get 48, that would get you your 0. So that's always a way to double check to make sure that you're going back and getting that 0.